Welcome everyone. The question is from the electromagnetic induction. The dimensions of the self-inductance are, four options are given. Which one is the correct one? We have to find it out. For that purpose, let us write it down. What is self-inductance? Here is a coil. And the current is flowing through it. Not the steady one. The current is which is changing with time. If the current is changing with time, then what will happen? When the current is flowing through this coil, then what will happen? If I take one of the rotation, one of the turning, we can say, so the current is flowing like this. Okay, so when the current is flowing like this, at that time, in the magnetic field is generated. Okay, and since the current is also changing with time, so the magnetic field is also changing with time. Okay, this coil have some area. This turning have some area. Each and every turning have that area. Let us say take is the uniform cross section. So the magnetic flux linked with this turn, we can say Bt into A. As the current is changing, the magnetic field is changing. As the magnetic field is changing, so the magnetic flux is changing. And Faraday's law says that whenever there is a change in magnetic flux linked with a coil or something, the EMF is induced. And Faraday's second law says that the EMF induced is the time rate of change of magnetic flux, that is d phi dt, but with a negative sign. So if I put it there, then obviously here what will happen? That ddt of B T into A. Okay, Bt into A. Now if I just put directly what is the value of the magnetic field for a single turn of a circular coil here, then it will become mu naught multiplied by n into I. If there is n number of turns, then n. If there is a single turn, then 1. Okay, multiplied by A. Okay, not this I. This I is the steady one, so I am taking the small I, which is changing with time. Okay, so mu naught capital N, number of turns capital A, the area of the coil, all can be taken outside a differentiation because it is not changing with time, but the current is changing with time. Mu naught is not changing as a constant, N is not changing as a constant, A is not changing as a constant. So the thing comes like that, E, which is the EMF induced in this coil, okay, or the N turns of this coil, is proportional to the change in current. Proportional to the change in current. Then obviously it is mathematics allowed us that you can put a equal to sign there, and you can put a constant of proportionality there, and you can write it down the rest of the equation as it is. Okay, so E L di dt, that L, this L is the self-inductance here. Okay, so we have to find it out the self-inductance of dimension of the self-inductance. So we can use this formula. So L equal to E divided by di dt, divided by the change in current. Okay, now what is EMF? EMF is nothing but the work done. Dimension of the EMF is the work done. So if you want to find it down, the dimension of the self-inductance, so dimension of the E is a dimension of the work done. Okay, so L is the length, LT inverse is the velocity, LT to the power minus 2 is the acceleration, mass into acceleration is the force, force into displacement, that means L square. Here it gives you the work done. Di dt, I is not the fundamental one, but the current is the fundamental one. Okay, sorry, I is the fundamental one, so you can put A here, and T is the time. So this will become M L square T to the power minus 2. If this T goes up, then it will become simply again that T will be multiplied and A inverse. Okay, so this will become M L square A to the power minus 1 and T to the power minus 1. So the option B is the correct option. Thank you all of you.